Now that we've talked about conditional probability, we're going to look at applications of Bayes' theorem, which we use for revising a probability value based on additional information that is later obtained. We're going to look at an example that started for us first. Assume cancer has a 1% prevalence rate, meaning that 1% of the population has cancer. Denoting the event of having cancer by C, we have the probability of cancer equals 0.01 for a subject randomly selected from the population. The result is included with the following performance characteristics of the test for cancer. They tell us again that the probability of having cancer is 0.01. The false positive rate is 10%, and the true positive rate is 80%. We're asked to find the probability of cancer given a positive test result. The solution using Bayes' theorem gives us the table below, and sometimes we'll also add in a total row at the bottom to total our columns. Now with Bayes' theorem, we actually build this table based off of the percents that they gave us. The first step in Bayes' theorem is to pick a large multiple of 10 as our population. Having a number for our population is going to make our life a lot easier than trying to deal with all of the percents. When I say a large multiple of 10, we typically think of like 100 or 1,000 or 10,000. You can go as large as you'd like. Then we use the information that they gave us to figure out the rest of this table. So the first thing they told us was that the probability of having cancer for the entire population was 0.01. Notice it's of the entire population, so that's of our 1,000 people. That's where this 10 is coming from. So I'm going to take that 0.01 and multiply it by the total population to get the 10 people that have cancer. To figure out this 990, we can use subtraction. We'll do the total population minus the 10 that's already in that column. That gives us our 990. To fill out the inside of the table, we have to look at some of the other information. So they tell us that the false positive rate is 10%. So if we're looking for our false positive, that's right here with that 99. So that's the next step that we're going to do. Now notice the false positive. If we look at the explanation, it's a positive test result given that cancer is not present. So we're not looking at the entire population anymore. We're only looking at the people that do not have cancer. So we have to take 10% of the 990 people that do not have cancer. Then just like we did before, to figure out the other part of the row, we subtract. So we'll take the 990 people total in the row and subtract the 99 people that did not have cancer and had a positive test result. Then we'll look at this true positive rate of 80%. That's right here. Just like before, we're not taking 80% of the total population. It was a positive test given that cancer is present. So cancer was only present for 10 people. So we do the 0.8 times 10. And then to figure out this last part of the table, just like we've done before, we take the total number of people in the row and subtract out the 8 that we've already figured out. You can get these black totals that we wrote in before just by adding. Now if we try to actually answer the question, they told us find the probability of cancer given a positive test result. So if we look at just the positive test result column, there's 107 people total there. Within that column, the people that have cancer, there's 8 of them. If we divide that out and round to our 3 significant figures, we'll have that it's about 0.0748. That's our probability of having cancer given a positive test result. Now, part of what we just dealt with was prior probability and posterior probability. A prior probability is an initial probability value originally obtained before any additional information is obtained. The posterior probability is a probability value that has been revised by using additional information later obtained. So if we look at that example, the probability of having cancer being 0.01 is prior probability, right? That was the original population. And then they give us information about the test result. So that probability that we found from the table of having cancer given a positive test result is a posterior probability because it uses the additional information. Now, let's look at an example from scratch. It says in Orange County, 51% of the adults are males and 49% are females. One adult is randomly selected for a survey involving credit card usage. For Part A, they tell us find the prior probability that the selected person is a male. So if we look here, they tell us that 51% of the adults are males. So the probability of picking a male is, in decimal form, 0.51. That is our prior probability. If we look at Part B, they give us extra information. They tell us it's later learned that the selected survey subject was smoking a cigar. 9.5% of males smoke cigars, whereas 1.7% of females smoke cigars, based on data from the Substance Abuse and Mental Health Services Administration. Use this additional information to find the probability that the selected subject is a male. So here, we're going to have to set up a table. So we have two different things going on here, male and female, and smoking a cigar and not smoking a cigar. So I'm going to put males in this column, females in this column, and I'll say smoking a cigar goes here, and not smoking a cigar goes here. Now notice I added in an extra row and an extra column. I'm going to make that my total row and my total column. Please note it doesn't matter which way you set up your table. If you wanted males and females to go vertical, that's perfectly okay as well, as long as you have your smoking cigar and not smoking cigar horizontally up top. So if we look back at that prior probability, they told us that 51% of the adults are males. So first I need to pick a total. I'm going to stick with 1,000 because it's what we chose before. Then to figure out my total number of males, I'm going to do my 0.51 times 1,000. That tells me that there's 510 males. To find my females, I'm going to do my 1,000 minus 510 to find that there's 490 females. So that's from my prior probability. Now, I look at the extra information they gave me. They told me that 9.5% of males smoke cigars. So I'm going to focus in on males and smoking cigars, which is my top left-hand square. 9.5% is 0.095, and it's of males. So I'm going to multiply by the 510 total males. That gives me 48.45. Do not round, because if we had picked a larger total number, if we had picked 10,000 or 100,000 or 1,000,000, we wouldn't have decimals after, or numbers after our decimal point. So we never round when we're using Bayes' theorem. If we figured this out, we can figure out the males who do not smoke cigars with subtraction. I can take the total number of males, subtract the 48.45, and get 461.55. Now I can look at this 1.7% of females smoke cigars. So that's 0.017 for my females in smoking cigars times the total number of females, that 490. That gives me 8.33. Just like before, I can use subtraction. So I'm going to do the 490 total females minus the 8.33 that smoke cigars, and that tells me that 481.67 do not smoke cigars. You've probably noticed a pattern. In general, we multiply once to figure out a row or a column, or a box in a row or a column, and then we subtract to find out the other part. Just like I did before, I'm going to total what's left because it may help me find out whatever probabilities they ask me. So if I add straight across this column, I'll get 56.78. And same thing if I add across this row, 943.22. Now we can answer the question that they asked. They asked us to use this additional information to find the probability that the selected subject is a male. And the additional information is that they were smoking a cigar. So what they're really asking us to do is to find the probability that it was a male given that they're smoking a cigar. So if we look here, smoking a cigar is this first row. So that means my denominator is going to be 56.78. Within that row, there's 48.45 males. If we divide that out and round to 3 significant figures, we'll find that the probability is about 0.853.